Okay, you should open your packet to page 11 and do both of these graphs and all of their behaviors. You can graph them on your calculator because you will have a calculator on your quiz on Wednesday. We'll pause the video here and give you about 5 minutes to do these two graphs. Okay, so if we graph x to the fourth, looks like this, through the origin. So the domain is all real numbers. The range is y is greater than or equal to 0. You could write it with interval notation like that. Left end behavior is x goes to negative infinity, y goes to infinity, and x goes to infinity is right end behavior, y goes to infinity. It is even because it has y-axis symmetry. It is continuous. If we walk on the graph from left to right, we are decreasing from negative infinity to 0, or you can say x is less than 0, and then the graph is increasing from 0 to infinity, or you can say x is greater than 0. The x-intercept is at 0 with the y-intercept of 0 because it's on the origin. There is a absolute minimum at 0, and there are no asymptotes. Now for the square root of x, or x to the 1/2, your graph looked like this, with the endpoint on the origin. So the domain is x is greater than or equal to 0, or you could do 0 to infinity. The range is y is greater than or equal to 0, or you could do 0 to infinity. There is no left end behavior. Since end behavior is going to negative infinity, the graph doesn't go to negative infinity. It stops here at the origin. So there is no left end behavior. But for right end behavior, x goes to infinity, y goes slowly to infinity. It is neither odd or even. It is continuous. The whole graph is increasing, so we would say 0 to infinity, or you could say x is greater than 0. No decreasing. X and y-intercept of 0. There is an absolute minimum at 0, since that is the bottom of the graph, and there are no asymptotes. And if you used your grid at the bottom, you could have graphed more accurately than my little sketches at the top. So 0 to the 4th is 0, 1 to the 4th is 1, 2 to the 4th is 2 times 2 times 16. I don't have enough room. I'll call this 16. I'll go each of these by 2. And you could have actually made a bigger graph than I sketched at the top. For the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and you get your slowly increasing graph. So if you turn to page 12, we're going to graph and compare and contrast more power functions today. So on this grid, we are going to graph x to the 1/3, x to the 1/2, x squared, and x cubed. You can use your calculator to get a table of values. Since I'm making this video, I will use my calculator on the side and plot my nice points. Sorry, you won't be able to see it on the screen. Okay, so for x to the 1/3, that's the cube root of x. That starts at 0, 0. And then 1, 1. Whoa, that is huge. Sorry. I thought I would make graphing easier. Let's try that again. 0, 0, 1, 1. That's nice now. And then the cube root of 8 is 2. So when I connect the points for the cube root, it is slowly increasing to the right. Then we've got x to the 1/2, which is the square root of x. That also is at 0, 0, 1, 1. The square root of 4 is 2. The square root of 9 is 3. Let me do that a little thinner so you can actually see what I'm drawing. And then let's do x, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Let me get this straight line. And then x squared, 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. So now we're increasing much more quickly. And last but not least, x to the third. 0 to the third is 0, 1 to the third is 1, 2 to the third is 8, and then 3 to the third is 27. That's way off my grid. And that increases fastest. Okay, what do you notice and what do you wonder? Let's go to B. What features are the same for all graphs? They all, we'll pause the video here and give you 1 minute to write down everything that you see is the same. Okay, did you say they all go through the point 0, 0, and 1, 1? They're all increasing. And then for differences, I would say their steepness are different, or the rate at what they're at which they're increasing. So for example, if we were going to compare x to the third is increasing the fastest because it has the highest exponent, where x to the 1/3 is increasing the slowest because that has the smallest exponent. Another difference is the inverse functions. So let's see, the inverse functions. So x to the 1/3 and x cubed are inverses of each other. They undo each other. Well, their graphs reflect over the line y equals x here. So if we folded the board across this line, x to the third would line up with x to the 1/3. So they reflect over the line y equals x. So we'll write that. Oops. Inverses reflected over y equals x. Okay, so the difference between the graphs that curve up and the graphs that curve down. So our two graphs that curve up are here, the x squared and x to the third, versus the graphs that curve down are x to the 1/2 and x to the 1/3. So think to yourself, what is the difference between those power functions? And we can generalize that by saying when the exponent is greater than 1, it curves up. And when the exponent is between 0 and 1, because we didn't get into negative, so let's say, I don't know, pick a n for exponent. So between 0 and 1, it curves down. How are x to the 1/2 and x squared related? Ooh, we already talked about that. They're inverses of each other. Okay. On page 13, now we have negative exponents to talk about. So again, we're going to graph these in our calculator. So we'll pause the video here for you to make these 5 graphs. And to make it easier, I actually took pictures of my calculator screen so you could see my table of values. I did y to the -3 in y1, this one in y2, this one in y3, y4, and then y5. And I had to scroll over to be able to see the all 5 at the same time. But now to plot my points, so let's start with x to the -3. There is a vertical asymptote for all of them. So here we'll draw a dashed vertical asymptote. There is a horizontal asymptote as well, because those negative exponents mean a fraction. For example, x to the -3 is equal to 1. Wait, that looks horrible. Hang on. X to the -3 is equal to 1 over x to the 3rd, so that's why x cannot equal 0. So if we plot that, and they only give us integers here, so we'll have to approximate our decimals. 1, 1 is a nice point. 2.125. And then 0.03, that's really down there. Now, if we look between 0 and 1, it's just going to approach the x-axis. And what I could do in the table is change it to half units, but I'm not going back to take those pictures again. Actually, instead what I'll do is I'll do 0.5 to the -3 just to see what that comes out to. That's 8. So at 1/2, we go all the way up. Here's 1/2, up here at 8, so it's way off the screen. So that increases fast there. Okay, so now let's do x to the -2. That's my y2. Again, we go through 1, 1. And then 2 1/4, which is bigger than the 0.125, so that's go there. I know that looks more like a half, but that's okay. And then 0.11, so these y values are higher than the y values in y1, and if we do 0.5 to the -2, we get 4. Ooh, I can actually graph that. And then we'll do x to the -1, 1, 1, a half. So these, again, these values are greater. So let's do 0.5 to the -1. That's 2. And then y4 is our x to the -1/2. Again, 1, 1, that's a popular point. Then 0.7, so those are higher. I bet this will be lower, so let's do 0.5 to the -1/2 is 1.4. So let's say about there. This is getting crowded. Okay, and the last one, x to the -1/3 is our y5. 1, 1, 0.79, so that's even higher. I wish I hadn't left more room. Let's do 0.5 to the -1/3. And that's 1.25. Okay, oops, I crossed my asymptote. Not okay. Don't cross an asymptote. There we go, that's gonna go up. Let's see what questions they want us to answer. Oh, no, no, no. I want the whole thing to move. Okay, I fixed it. That was scary. All right, so the whole thing moves. What do you notice? What do you wonder? No, we're skipping that. List the features that are the same. Okay, take 2 minutes in your groups. List the features that are the same. Oh, and while you're at it, do the differences, and then we'll unpause the video and go through them. So for same, did you say they all go through the point 1, 1? There's a vertical asymptote at x equals 0, a horizontal asymptote at y equals 0. They're all decreasing. And they have similar shapes even though they're decreasing at different rates. So that's my answer for C, would be their steepness and how quickly they're decreasing. More functions to see what they look like. So we will pause the video for you to graph them in your calculator. I would look at the shape and maybe look at a table of values to see some nice key points. Think about, we kind of did this yesterday or Friday, sorry, where we then talked about their symmetries and their quadrants and their end behaviors. So we'll talk about some properties once they're all graphed. When you put the equation in your calculator, you must put parentheses around the exponents. So we'll pause the video here for you to graph all 6 graphs while I do the same. So for number 1, I see that we have some nice coordinates at, let me make this bigger. That's better. We have some nice coordinates at 0, 0. 1, 1. And then if you look all the way out to 8, we get a nice coordinate at 4. And then if I look at the graph, I see that it's symmetric with the y-axis. So we get this kind of shape where we increase to the right, but then the left is decreasing. Kind of looks like a bird. Then for number 2, x to the 4/3. The only nice points that really fit are the negative 1, 1, 0, 0, and 1, 1. Because then when you look further out, they're all decimals. 8, we get 8, it's all the way up there at 16, so it increases pretty quickly. You know what, 2 goes to 2.5. Can put that in there. When you connect these dots, do not do them in a straight line, because if you look at the graph to see the shape, you can see it's slightly curvy, so make it slightly curvy. Now the third one's unique because when you graph it, you only have graph in the first quadrant. 0, 0, 1, 1. Let's see what other nice points we have. There's 4, 8. And then it's off the graph, so we'll go up like that. So that's interesting. Well, we'll get to that at the bottom. All right, let me finish graphing and then we'll look at the differences and the similarities. Okay, so for x to the 3/4, we've got 0, 0, 1, 1 again. And then it's slowly increasing. I don't see any other nice ones. So let's do, I don't know, it looks like at 5, a little more, like 3.3. I'll go like that. Because around 10 is at 5.6, so that's good enough. All right, the next one, x to the 3/5. Now we have graph in 2 quadrants. So we have these 1, 1, 0, 0, and -1, -1 graphs, and none of the others are nice. They're all decimals. So if we're at 7, we're near 3, approximately. So the -7 will be near -3. That gives that slowly increasing shape. And last but not least, x to the 5/3. When we graph that one, we still get our nice points at -1, -1, 0, 0, 1, 1, but this one increases faster because when we're at 3, you're near 6, and then 4 is near 10. Same thing with the negatives. So it's a more steep S shape. Okay, so in comparing all of these graphs, looks like just 2 of them have that first quadrant where they have an endpoint. So what's different about this graph and this graph that they have an endpoint and they're not, they don't have any left end behavior? I see it. Look at the denominators in your power. They both have an even denominator. The 2 and the 4 are even numbers, where here the denominator is a 5, a 3, a 3, and a 3. So these even denominators have a restricted domain where the graph is greater than or equal to 0. So let's write that down. Whoa, too big. Okay, even denominator in power is a restricted domain. X is greater than or equal to 0. What else? The graphs that increase faster. So let's compare the graphs that all have a 3 in the denominator. So this one, and this one. The 5/3 is a steeper graph than the 4/3, which is steeper than the 2/3. But then it's interesting, the 5/3 has the odd symmetry, where both of these graphs are even. And the difference there is the numerator. So when the numerator is odd, you have the odd symmetry. Same thing here. Check that out. When the numerator is even, you have an even symmetry with the y-axis. But the bigger the numerator, the steeper. Well, let's write that. Bigger numerator is steeper. Okay, so your homework is page 15 and 16. You have to graph them, definitely use your calculator, and fill in all the properties just like the warm-up.